Hi everyone. In this video, we're going to be talking about properties of solutions. Now, the properties we're talking about are particle size, and we have some definitions to describe the size of the particles in a solution. And so we use the term solution, colloid, or suspension for the different sizes of the particles. So solutions are transparent. You can see through them. They may be colored, but you can see through them, or light shines through them. They do not separate, and they contain small particles. Emphasis on the small. Those particles could be ions or molecules, and they pass right through a filter, and they pass right through membranes. Now, colloids have medium-sized particles. They can't be filtered, but they can be trapped by a semi-permeable membrane. Now, some examples of colloids are like fog or smoke or milk or butter. And blood plasma is actually a colloid as well. Now, suspensions are heterogeneous, meaning you can see the particles. So if I take a handful of dirt and throw it in a cup of water and stir it up, the dirt doesn't really dissolve in the water. It's suspended. It's like kind of floating for a minute. And so we call it a suspension. But if I let it sit for 5 minutes, the dirt will settle to the bottom of the cup. And so suspensions have large, very large particles, and you can filter them, right? If I put muddy water through a coffee filter, the water will come through, but the mud will stay in the filter. And so some examples of this include blood platelets, muddy water, like a fruit smoothie, right? So the flow chart here, solution has small particles, colloid has medium particles, and a suspension has very large particles. Solutions and colloids never settle. But suspensions, if you leave them sit, the particles will settle to the bottom from gravity. Now, solutions pass right through filters and membranes. Colloids pass through a filter, but not through a membrane. And suspensions don't pass through either. So here's an image showing if you had big particles in red, medium particles in green, and little particles in orange, right? The filter will trap out the big particles, and then the semi-permeable membrane will filter out the big and the medium particles. I don't really like this image, so I made this really terrible one by hand, but it's trying to illustrate the same point. So a filter is like a screen with big holes, and a membrane is like a screen with really tiny holes. And so solution, because it has tiny little particles, will pass right through both of them, and you'll have your particles on the other side. Now, colloids have medium-sized particles, and so they'll pass through the filter, but not through the membrane. And so you'll have your medium-sized particles, trapped there. And a suspension has gigantic particles, and those can't go through the filter. So solution, little particles, goes through filters and membranes. Colloids, medium particles, goes through a filter, but not a membrane. And a suspension doesn't go through a filter. Now, study check. A mixture that has solute particles that do not settle, but are too large to pass through a membrane. Well, that would be a colloid because they're too big to pass through the membrane, but they don't settle. And so only suspension particles are big enough to settle. All right. So the next topic we're going to talk about is osmosis. So osmosis is this unique property where water molecules move across a semi-permeable membrane from a region of low solute concentration to a region of high solute concentration. And so let me zoom this in so we can see it a little better. Imagine this wafer here in the middle of the beaker is a semi-permeable membrane, meaning the solute particles can't get across, but water molecules can because the water molecules are small enough. And so what'll happen is in order to dilute the solute particles, the water molecules will move across into the side where the solute is. So the water is going to be moving towards the particles. And that's the definition of osmosis, the movement of water across a semi-permeable membrane from a region of low solute concentration to a region of high solute concentration. Now, the water trying to move over here makes this side of the beaker want to increase in volume. Osmotic pressure is the amount of pressure you would have to apply. So if you had like a piston over here, if you could apply a downward pressure on this side of the beaker, the amount of pressure you would have to apply to stop osmosis from happening is known as osmotic pressure. So it's equal to the pressure that would prevent the flow of water due to osmosis. Now, what would happen if we applied a lot of pressure on this side, more so than the osmotic pressure? Well, you could squeeze water molecules the other direction if you apply enough pressure. And that's what we call reverse osmosis. So reverse osmosis, you apply a greater pressure than osmotic pressure, and you force water molecules to move away from the solute. And this is actually how we purify ocean water. And so a lot of countries in the Middle East, like the United Arab Emirates, they don't have a lot of rainfall because it's a desert. And so how they get their fresh drinking water is they take ocean water and they pressurize it through a semi-permeable membrane, and only the water gets through, and the salt and other solute particles get trapped. And so they get fresh drinking water out of the other side. Certain companies use this as well. I think Dasani uses reverse osmosis. If you look at the back of your water bottle, it'll say purified by reverse osmosis. And they're just talking about this function of pressurizing water across a membrane. So now that we've talked about osmosis, let's talk about what happens to a cell, specifically a red blood cell, when you place it in different solutions. So the word isotonic means same. And so we mean that the concentration of particles in the solution here is the same concentration that's inside the red blood cell. And red blood cells have about 5% glucose and about 0.9% sodium chloride. So that's the concentration inside the blood cell. So if the solution outside had this same concentration as inside, we would say that it's isotonic, and osmosis would not occur because the concentrations are the same inside and out. Now, a hypotonic solution is a solution that has a lower solute concentration. Now, if we put a blood cell or any cell in a hypotonic solution, what happens is the water molecules want to go into the cell to try and dilute it because there's more solute, different color here. So there's more solute particles inside the blood cell than outside. And so osmosis makes water flow into the cell. And the red blood cells will swell with water and they can possibly rupture and burst open. And when a red blood cell bursts open, this is known as hemolysis. Hemo for blood, lysis for breaking open. Now, if we take a red blood cell and we put it in a hypertonic solution, that's a solution that has a higher solute concentration. That would be like salt water, right? We're saying that the liquid outside has more solute particles than the blood cell does. And so what happens there is the water from the blood cell wants to flow out into solution. And so the cell shrivels up. And this is known as crenation. So once again, isotonic means the same concentration inside and out. Osmosis does not occur. Hypotonic is a lower solute concentration, and so water flows into the cell. In a hypertonic solution, water flows out of the cell. All right, let's do a study check. Indicate whether each of the following solutions is isotonic, hypotonic, or hypertonic. And remember, we are comparing it to the internal concentration of a red blood cell. Oh, that's not what I wanted to copy. I want the text. There we go. All right, just for reference. There we go. This is what's inside of a blood cell. Okay. And so if we put a red blood cell in a 2% sodium chloride solution, we see that the 2% is higher than the 0.9. And so a higher concentration is hypertonic. A 1% glucose solution is less than the 5% in the cell. And so this would be a hypotonic solution. 0.5% sodium chloride is less than 0.9, so this would be hypotonic. And a 5% glucose solution is the exact same as what's inside the blood cell, and so this would be isotonic. Okay. And the last practice problem. When a red blood cell is placed in each of the following solutions, determine if there will be no change, hemolysis, or crenation. And so once again, I am going to copy this for quick reference. And remember, this is what's inside a blood cell. So if you place a blood cell in a 5% glucose solution, this is the same. So it's isotonic. So you'd have no change at all. If you placed a red blood cell in a 1% glucose solution, this is less concentrated. So it'd be hypotonic. And so it would undergo hemolysis. 0.5% sodium chloride is less than 0.9. So this would also undergo hemolysis. And a 2% sodium chloride is higher than 0.9. So this would be a hypertonic solution. And so the cell would undergo crenation. All right, so to recap this video, we talked about solutions, colloids, and suspensions, and that's based on particle size. Solutions are tiny, colloids are medium, and suspensions are very large particles. Osmosis is the movement of water molecules from region of low concentration to a region of high solute concentration across a semipermeable membrane. And then we talked about isotonic, hypotonic, and hypertonic solutions. Iso is when there's the same concentration, when there's no change. A hypotonic solution has lower solute concentration, so water goes into the cell. Hypertonic, there's more particles outside the cell, and so water goes out of the cell. That's it for this video. Thanks for watching. See you guys in the lab this week.